So for our afternoon talk today, we're very happy to have Mark Stern, who will come Instanton, Decay and Moduli.
Thank you. It's a pleasure to be here. Thank you for the invitation, including my collaborators not here today. All right, so today I'd like to talk about some joint work, or pieces of joint work. So with two different collaborations. One is with Sergei Cherkis on Andreas Lorraine. And the other is with Travis Maxfield and Savdeep Sethi. Okay, so lest I forget later on. All right, so I'd like to talk about the decay of instantons, and I was asked during lunch to assume a little bit less physics in the last talk. So I'll start a slightly more elementary spot, which probably suits my background better. And just remind you that if you're in, say, R3, and you have a compactly supported charge, then you have immediately that the electric field, say it's a static charge, for example, this is R3. If you have a static charge, the electric field decays like a constant over R squared, and life as we know it wouldn't exist without that decay. So this is a fundamental fact that we learn in I don't know, high school. And it's easy to, because electromagnetism is governed by linear differential equations, it's easy to extend this result to more physically reasonable spaces. And so physicists and mathematicians have long wondered what the corresponding correct decay rates are for the nonlinear generalizations of Maxwell's equations that dictate your other nuclear forces. And in the case of what? So these are, of course, the Yang-Mills equations. And the question of understanding decay of, say, instantons in Yang-Mills has kind of been an obstruction to properly constructing moduli spaces and understanding moduli spaces in Yang-Mills. People often have to sort of add ad hoc assumptions to make sure the decay is what they need it to be. So today I want to make some partial progress in removing those ad hoc assumptions and sort of understanding correctly what is the nature of decay. And I'm not going to do, given the audience, I'm not going to do a lot of analysis at the board. I'm just going to describe some of the issues, some of the results, and make a few comments about some techniques for attacking them. Okay, so let me start, I guess, at the beginning with the Yang-Mills equations. So we're going to start with, I guess, we'll let E be a CK bundle. So we'll just deal with the unitary group for now. But there's nothing special about the unitary group for this discussion. Let's say over a Riemannian. And I'll stick to 4 manifolds today. And I guess it needs a name. Riemannian 4 manifold M. And I want E to have a connection. So E is Hermitian with a Hermitian connection, which, depending on the mood, I'll denote by A, or usually the associated exterior derivative of dA. All right, so A or dA will denote my connection. dA, again, typically means the exterior derivative associated with it. And then, of course, we have associated with the exterior derivative, we have its associated curvature. We have FA, which is dA squared. So the Yang-Mills energy is usually given as 1/2 VL2 norm squared of the curvature. And physical processes are, of course, governed by, as we were hearing in the last talk, the minima of this energy. And so we most want to know the behavior of fields which minimize this equation. And so the Euler-Lagrange equations for the critical points of this are known as the Yang-Mills equation. So the Yang-Mills equation can be written as the exterior derivative of the Hodge star of the curvature vanishes. And as an analyst, it makes me uncomfortable to ever write this equation without writing also the Bianchi identity next to it. So this is, of course, true for all equations, all fields independent of, this is just automatic for the curvature, the Bianchi identity, and I'll typically call these coupled equations the Yang-Mills. I'll sort of absorb Bianchi into it, because of course these two equations together give us an elliptic system for the curvature. So as an analyst, I prefer to always having an elliptic system present. So, of course, there's an obvious symmetry here under the Hodge star operator. And since we're in 4 dimensions, we can decompose the curvature, or any other two form, into a self-dual part and an anti-self-dual part. So Hodge star. And we have the definition, working definition is that a connection is called an instanton. In 4 dimensions, if FA is equal to FA plus or minus, it's either self-dual or anti-self-dual. And then of course,
One of your collaborators just arrived, I think that's what
good thing I saw you. So you're already up there. Started that. Okay. So A is an instanton if we say it's an instanton if it's self-dual or anti-self-dual. All right. So when instantons exist, we all recall that they're minimizers. Let's see how this goes. Use this one. All right, I think I did that in the wrong order. Okay, this we'll figure it out. Maybe.
I'll bring you a chair.
All right, that was confusing. I think I'll have to use the eraser next time.
Push that one up higher.
No, because I want to be able. Oh, yeah, that would work too. All right, so. Okay, so anyway, maybe I spent so much time with that. I won't remind you all that we can use. We have some. Pardon? We have it. The instantons are always on a compact manifold. Instantons are always minimizers of the Yang-Mills energy. Okay, so as I said, so the instantons then are once again since they're minimizers, they dominate physical processes, and we want to understand them better, and we want to understand their moduli space, as Professor was saying that last time. And now, the cases of most interest to physicists are probably the gravitational instantons. I learned a lot about those from Hayo's excellent talk. But so I won't be dealing with some of the more exotic ones that he was dealing with, and some of those I think would be pretty hard to hit with the analysis that we're using here. But the spaces that we're most interested in probably are first the ALE spaces. And these guys, as we learned last time, have quartic volume growth. And they're asymptotically of the form, so R4 mod discrete group.
So you mean this is the choice of M?
Yeah, so I'll be discussing various choices. And this case is well understood already, but I thought I'd start with the well understood case. Somehow the problem is subcritical in that case. There we go, we have let there be light. And the case that I'll probably talk the most about is the ALF spaces. And as we learned last time, these have cubic volume growth. And what else do I want to say? They have Riemann curvature decay which is cubic also. And they're asymptotically circle bundles. Over R3 or R3 minus 1, as I was reminded last time. I might have left that last one out if I hadn't been reminded. And now I'm going to deviate from higher.
Z2.
Thank you. That's what I meant to say. That was a chocolate. All right, so now I'm going to deviate from Hyo's focus and look instead. Sorry, I'll try to light that up. But then I have to crouch here, which is what I was trying to avoid.
That's fine.
All right. So then the other cases. So we learned yesterday that there are too many difficult cases here, so I'm just going to give a non-simply connected example where a lot of work has been done. That's R2 cross T2. Okay, so this is the case of doubly periodic instantons, and I don't have to describe the asymptotic geometry of that. And finally, the most mysterious case with the simplest geometry, R cross T3. Okay, so these are all spaces where there's been a lot of study of instantons, and there's been a lot of questions arising about the nature of their decay. So I want to start off and give you some linear intuition, which will be faulty in the ALE case because I don't want to do the Lie theory sufficient to make that complete. I'll just give us the answer later on there. But let's look at what our linear intuition tells us the decay should be. Okay? So our linear intuition, well, first we have the Yang-Mills equations. So right now I'm going to deal with Yang-Mills, not instanton for the linear intuition. So Yang-Mills equations imply the following. So we have a second order Bachner identity. And Bachner identities are crucial in this. So we have, what is it, something like nabla star nabla Fa plus, I guess, FIP, I'll use it in a local orthonormal frame, FPJ, WI wedge WJ, plus something like RIP FPJ, plus RIPQ JFPQ, WI wedge WJ. For those of you who want the whole thing. So you have a standard Bachner formula that you all can derive in 5 seconds. And it equals 0. Thank you. Yes. So we have it. So the fields satisfy this Bachner identity. And so the Bachner identity.
What is W? That's a frame?
Yes, I said in local orthonormal
And that's
frame.
the W.
Pardon?
And the W is the frame, yeah.
It's the coframe, yes.
Co-frame.
So coframe there, frame here. Okay. So I never like to put in GIJs at the board. Just always work orthonormal. All right, so this is the nonlinearity in the discussion, right? So we have a quadratic term here, which is essentially where all our problems arise in Yang-Mills field, in Yang-Mills theory. And this quadratic term is going to cause us trouble. So let's first see what happens when it's not there. So if k equals 1, for example, or more generally, if we're dealing with an abelian gauge group, then this term is 0. And so then we just have FA is simply a harmonic 2 form. And we'll get our intuition. So I took the simpler examples of these gravitational instantons because I wanted deal with a case where the base space was clearly related to some Euclidean space. And the intuition for our growth is always going to come from the base space. Somehow the fibers are not going to strongly affect our growth data. It's just going to be related to volume behavior. And so with our, I'm going to be, when I look at these spaces, I'm going to be thinking this is R4. My analysis for ALF will be thinking of R3, R2, and R1, etc. So if F is a harmonic two form, in particular strongly harmonic, so that by that I mean dA plus, or let's say d plus d star equals 0. If we have something that's harmonic in the strong sense, as in the kernel of this, then we know that whatever the degree of the form is, if it's L2, then we have that F decays like 1 over R to the n minus 1. Well, of course, that's not L2 in all the dimensions we're looking at. Certainly, it's L2 for, I guess, n equals 4. That gives you 1 over R cubed for n equals, so for case 1, we get 1 over R cubed. For case 2, we get 1 over R squared, and that's still going to be L2 on R3. And for case 3, we're not going to have anything, we're going to get 1 over R, so that's the R2 cross T2 case. That's not integrable. If we're still thinking about harmonics, the next integrable level would be 1 over R squared, so that we'll just say the first L2 harmonic, here I'm just thinking of L2 at infinity. Well, let's see. My board's use is not really good here. So is 1 over R squared. And there are no L2 harmonics for the line. So the line is always a problem, because linear theory gives us no suggestion for how this should behave. Right? So the line always ends up being a mystery in this context. So it's somehow, it seems like it should be the easiest object to deal with, but for some reason, for many reasons, the line, the R cross T3 is the most problematic. Okay. So, let's see. So let's see how good is our intuition. Well, first the ALE case. Well, our intuition would have been good if I'd gone ahead and used the fact that this is a two form in R4 instead of just an arbitrary form of arbitrary degree in Euclidean space, because two forms in R4 should actually asymptotically be decay quartically. So here we get quartic decay. So, so we have, I guess, that's the constant over R4. Again, here, I always have the background assumption in case I forget to repeat it every 5 minutes, that my my Yang-Mills fields are finite energy. They're L2. Okay, so that's always a background assumption. So in the ALE case, we have quartic decay, and we'll see later on that somehow that's subcritical, and that makes this not very delicate to prove. There are many different ways to prove this for ALE spaces, but in the simplest case of R4, I'll just give you a quick sketch. To see this in R4, we just use the fact that the Yang-Mills equations are conformal invariants. So if I have a Yang-Mills field on R4, it gives me one on S4 minus a point. So FA is Yang-Mills on S4 minus a point. Again, with the same finite energy, because the energy is invariant. And so if it's Yang-Mills on S4 minus a point, then Uhlenbeck's removable singularity theorem tells us we can continue it across the point. So we can smoothly And now if you go back and compare the S4 metric to the R4 metric, if it's smooth in S4, this implies, so smooth or actually continuous in S4, or bounded in S4 implies FA in the R4 metric is a quartically decay. So that's just a scale. Okay. And there, of course, you can extend this fairly readily to other fields, to other asymptotic Euclidean manifolds, and there are many folks whose names are attached to that: Uhlenbeck, Donaldson, Nakajima, Rade, and others. Okay. So next, let me say something about the ALF case. So the ALF case, remember, our intuition was that the linear approximation, which is actually good in this case, so I gave the optimal harmonic statement for R3. There we had 1 over R squared decay. We expected 1 over R squared decay. And this 1 over R squared is the critical level for decay in these Yang-Mills problems for reasons that we'll make clear later on. And it's much harder to prove 1 over R squared decay when you expect 1 over R squared decay than to prove 1 over R4 decay when you expect 1 over R4 decay, even though it's less decay. This level of decay is important for many aspects of studying the moduli space. And we'll say a little bit more about that later. But so first, let's see that anything we have to prove here has to be sharp. So let's specialize to Taub nut, multi-center Taub nut, since it's already appeared in 2 out of the previous 2 talks, so it might as well come again. So I'll write that for K-centers, I'll write as T and K. And so remember, this has the familiar metric. So we have, we'll write the metric as V, the x squared plus V inverse, theta plus omega squared. And here, this is a standard metric. So I'm writing a metric for a circle bundle over R3, a degenerate circle bundle. So not actually a full circle bundle, but we have, this is going to be the standard metric on R3. Oops. Here. And so I have a circle bundle. So this is an angular variable plus a connection term. And then V has, I'll just give a simple form of it, has something, there are various ways to do this, but I'll just write it as 1 plus some 1 over x minus pi, I running from 1 to k, and pi is just k points in R3. Okay, and so you can change the scale here and here. Otherwise, this is sort of a standard structure of Taub nut. And at each, there's a line bundle associated with each point pi. And, or you could, yes, I can think of it that way. And each of those line bundles comes canonically equipped with a connection. And that connection is, we can give Taub nut an orientation so that all of those line bundles are anti-self dual. So there exists line bundles, call them LQ1, LQK, equipped with ASD, anti-self dual connections. And the curvature of those connections all decays quadratically and no faster. So this is kind of scary for an analyst. I want to prove something decays quadratically, and usually I want to have room left over. I'd like to show it decays quadratically if I really think it decays like 1 over r3 halves, you know, because I always like to have or 1 over r log over r squared or something. Because this is has a sharp. I mean, our linear intuition seems to be pretty sharp here. We can't do any better than it. Okay, so
I mean, the curvatures are just harmonic too, right?
the curvature are harmonic two forms.
So, I mean, the linear intuition is, I mean, the answer is the linear, it's the same as the linear.
Yes.
Yeah.
That's exactly correct. But we're not. Yes, that's true. So we're of course not exactly on R3, but nonetheless,
No, right.
it's a linear problem, and you're right that the linear problem on something with this geometry is an easy problem. Yeah. So, but we want to know this. But I mean, we want to know this for the nonlinear problem.
Sure.
And in the nonlinear case, you have a little bit more. Anyway, so let me give you a result in this case first. So we do a theorem with Sergey and Andreas Lorraine and myself. And that says that let's let A be a finite energy instanton on, say, P and K. And I'm gonna, let me put an assumption here, and I'll explain the assumption after I complete the statement of the sentence. That's not the theorem. So let's assume generic asymptotic holonomial. Well, let me actually, I guess I can say what that means now. So that means, no, let me actually hold on first. And so then there exists C greater than 0 such that the curvature decays quadratically. Okay, so we have the desired curvature decay. And here the generic asymptotic holonomial statement is somehow easy to state. So we have the holonomial around this S1 fiber, and what I want is that the following is true. So the centralizer. So generic asymptotic holonomial implies is equivalent to the following statement: is that for large radius, the centralizer of the holonomial around the fiber is a maximal torus. So that's the generic state. If you take any generic element in the Lie algebra, its centralizer is a maximal torus. Okay? So under that extra assumption, we get the quadratic curvature decay. Now, in the case of R2 cross T2, I don't understand that case very well yet. So let me say a little bit about what's been done there. I was doing some homework beforehand, but I don't completely understand some of the papers that have been written on this so far. But let's see. So R2 is a funny case. So we're going to be, for analysis, R2 is often a two-dimensional Euclidean space is often bizarre. It's dimension 3 and above, and dimension 1 are different from dimension 2. Even in that you have Green's functions that become logarithmic, etc. in dimension 2. I picked up the wrong page, so where did that go?
So this last condition, is it very restrictive?
Pardon?
The last condition.
This?
Yeah.
What about it?
Is it very restrictive?
As I said, it's generic. So if you perturb anything, it should be that condition. But it's saying what it's forbidding is, for example, that you could have an element centralizer who's I mean, I would say
It's generic in what, the position of the points?
No. So I have
What's varying here?
sure. Okay. So I have
Actually.
a holonomy.
Oh, the connection.
Yes. So I have holonomy around the connection around, and so I've got some element UK. So I've got eigenvalues lambda 1, lambda k, and I basically well,
You
let's
want
see.
to feel distinct. You want them to be
Distinct
no?
mod 2 pi
Oh, yeah.
times n. Yeah, so I need these guys distinct modulo 2 pi I z or something. Okay. So you could, for example, have, a block of ones and zeros, and you're going to have a non-abelian center, right? Just that'll give you block diagonalization. So certainly this is generic. And we've got information which I don't think I'll put at the board in this case. I'll talk about, for the non-generic case, I'll just discuss that in the R cross T.
No.
You need them bounded away from infinity as you go to, away from, I mean, they're staying
bounded.
distinct as you're going out to infinity?
They're
By
bounded.
some bounded amount?
Pardon me? These, so it's,
You could imagine as they go to infinity, they actually go and start coinciding.
yes, so I'm talking about, so asymptotically, so it's, you can show that, so let me see what I want to say here. Right, so I asymptotically want them to be distinct, so in a limit.
In the limit, okay.
Okay. Yes. This is strictly a limiting state. Okay, so let's see, back to the R2 cross T2 case, where a lot of work has been done on the moduli, some really nice work by Jardim and Bacard, and I believe some nice work also here by Hertevies and others. But we have
Sorry, can I just, sorry, can I just ask about this case? I mean, are those lambdas likely to be constant? For a
So-
given instanton with finite energy? Finite
So, what you can show is, well, this is jumping way ahead, but I wasn't planning on doing it anyway, so it's not really jumping ahead. So, once you show quadratic curvature decay without any assumption of constancy, then you can show that the holonomy has some form like this. There's some asymptotic form. I think you'd want a 1 over r squared here, but all we've been able to show is over log r squared. Okay, so this is sort of constant, constant plus first radial harmonic. And it'd be nice if we had a second radial harmonic, but it's close enough for government work. Okay,
Like a Caleron,
beg pardon?
like a Caleron.
And you expect there to be, does one expect there to be moduli space if you fix the lambdas? Are the m's integers here or? Do you expect a moduli space if you fix either the lambdas or?
The m's are quantized, so.
Right,
and
so if you fix the lambdas and the n's, do you get, I mean, there should be a moduli space with those fixed?
Yes.
Or is it unique, I mean, presumably you have a moduli space for, I mean, can you choose the lambdas freely? I suppose that's, I mean, are they really generic? I mean, is there a moduli space for any?
Yeah, so I'm gonna leave most of that to Sergey's talk on Friday.
Okay.
Yeah, so that's,
Sneak preview?
yes,
Okay.
he's my mentor in this case. All right, so where are we? Yes, I started to mention the R2 cross T2 case, where the analysis is, I mean, even though the geometry is so simple, the analysis is somewhat hard, is pretty hard. Here, again, there are various, so Jardim had conjectured quadratic curvature decay. And he and Picard had some nice work analyzing the moduli under that assumption. But there's a 2014 paper by Mochizuki which claims that that on R2 cross T2 you have that instantons decay unlike just the best you can do is constant over R to 1 plus A for some A greater than 0. And so he claims that Jardim's transform was missing instantons associated with objects you pick up from slower decaying objects. Okay, so
But does he have examples of things that decay slower?
So as I was writing this talk, I was looking through his 128-page paper, trying to work out exactly what he claimed, and certainly he has examples on the complement of a compact set, and but I haven't, I'm being recorded, I haven't read it carefully enough to understand yet whether is Picard here? Yes, sir. You probably read that paper. Does he get it out?
I've not read the paper.
Pardon?
I've not read the paper.
Okay.
It's very easy to produce examples near infinity.
Yes.
And then you can expect that there are solutions which this kind of paper.
Yes. So, all right. So that's. So then let me say something about the case for the geometry is. I guess you can't have simpler geometry than R2 cross T2, but it's still a case about which at least 3 books have been written, and so this is the case of R cross T3. And here's we said our linear intuition tells us nothing, right? So a linear, if we're just talking about linear harmonics, there are no finite energy harmonics in R. There's some folk conjectures that instantons should decay at least polynomially, or it's like follow some power law. We have, I guess, Rovka has an example that at least on a half line decays quadratically. But we have this theorem under an obnoxious assumption that I was trying to eradicate on the flight over here, but wasn't able to. So I'm still working on this one. But this is due to Max Fields, Seppi, and myself. And so here's the obnoxious assumption. So assume that the formal tangent space to the moduli space of finite energy ASD connections at some connection A is a very simple thing. It's finite dimensional. Okay, so presumably this is clearly always true. But I haven't given myself convincing proof of this. Then we have the following statement. Instantons on R cross T3 satisfy. So this is an A-dependent statement. I should be careful. So when I say instantons, I should really say under this an instanton satisfying this hypothesis satisfies FA is less than or equal to a constant times R to the A minus 4/3 for every A greater than 0. So I guess that better be an A-dependent constant. So probably that could be improved to log times r to the minus 4/3 kind of thing. Yeah. So
Where is this number from?
that's complicated. I don't think I didn't bring my notes enough to be able to get that aboard. It's not the optimal rate anyway. So let me tell you also, so for the instantons, so if we also assume, so I'll tell you a little bit about those numbers later, if you'd like. It didn't occur to me that people would like to know that, but I guess it's the obvious question. So if we also assume generic asymptotic holonomy, then the following is true. So here there is no generic asymptotic holonomy assumption. And there are similar theorems you could prove under similar hypotheses in the Taub-Nut case. Although I don't remember what the power law is in that case. But then we have FA substantial to the constant depending on A times R d minus 3/2. Okay. Now, it's really important that these numbers are, well, it's nice that if we're going to have polynomial type decay or monomial type decay, can I call it polynomial if it's not an integer? Pardon? Power law. If we have a power law decay, it's really important that that power is decaying faster than 1 over r, because I mean, somehow just for L2 you expect, I mean, L2 just suggests it should be something better than r to the minus 1/2, since we're just L2 on a line, or a line cross T3. But if you want to understand the moduli, you really would like to have some nice limiting connection. And it's quite possible, and people, I think, tend to ignore this fact a little bit, but it's certainly possible that you could, even though you have these things converging to flat connections, if you take subsequences, it's not a priori clear to me that they should all converge to a given flat connection unless you have control. So if
You need L1 control to do that, right? Because you're integrating from infinity.
if you just want to integrate input, right, so you just want to say, so to control limiting connection is nice to have FA less than the constant over r to 1 plus epsilon, epsilon greater than 0. So, because then you can say that if you can in a frame where A of GDR is equal to 0, so a frame that's covariant constant in the r direction, you can just write A of infinity is equal to the integral from, I don't know, some t naught to infinity of f of ddr dot ds. And if you have this sort of power law behavior, then this is a nice finite integral and you have a limit. If you don't do this, then you can have the following sort of behavior conceivably. I guess I can't assert that it happens, but if you don't, do I use this board again? I'm afraid of this board. So let's see. So I just make a simple couple of observations. So so the instantonic, so the Yang-Mills equation on R cross T3 can be translated into a geodesic equation for a geodesic on formally on a space of connections on T3. And if you have, and you're limiting, you're going to limit to some component of the moduli space of flat connections. here we have, so flat on the torus. So I'll use a little f for the torus curvature. So here we have, so an instanton on R cross T3 can be thought of as a geodesic going between two components of the space of flat connections and space of all connections. But you don't know that how it approaches. You might have this thing coming in and spiraling around and getting arbitrarily close. It's not clear it limits to a single flat connection. And so I don't understand the geometry of this picture well enough unless I have some control like this.
Is there a Voyage-Shavitz inequality here that will give you sort of extra decay?
I think you have to have the extra decay first. I mean, I don't think, I'm a little uncomfortable with the way that works. So you have to, so the answer is I don't understand the proper use of that yet. So I've heard a few people do that, but it seems to me unclear that it applies with these assumptions. But so let's just say I'm not sure about that. All right.
The fact that it's gradient will make it more useful.
Pardon?
The fact that it's gradient, that's a duality equation, the gradient will make it more useful than geodesic.
It's a gradient flow. Yeah, so, but I'm just saying here, still,
Geodesics can be complicated, but
Yeah.
since it's gradient flow, then
Right.
yeah, but it's still, it's still unclear what, how it works. Yes. Anyway, possibly.
Can I ask, how do the order, I mean, geodesic equations are usually second order in T, whereas the instanton equation you write down, you expect to be first order.
Yes, that's a true state. So the Yang, so I was a little bit sloppy there. The Yang-Mills equation, the Yang-Mills energy can be interpreted as the geodesic energy. So, yeah, so this is, I guess, more a statement about Yang-Mills than, in this case, than.
So how would you single out the instantons as what? From the general geodesics?
Well, this is, so this is something I wrote a paper back about several years ago. So you can show that if you have a Yang-Mills field, which has the lowest possible energy, so that means in particular you're connecting two different components of the moduli space of flat connections, then you can show it can be decomposed as a sum of instantons. Okay, so so if you're energy minimizing in this context, then you can always be decomposed into a sum of instantons. From the Abelian case, you have to be careful about the possibility of adding things.
Is there Chern-Simons number for this connection on the three torus? Is that what distinguishes the components?
Well, yes. So you have Chern-Simon. You have a situation where the Chern-Simon number, you fix some reference, the Chern-Simons number is different, but I prefer there are situations where you have, for example, the Chern-Simons number is different even mod z, and so you have so for example, for a case like G2 for SO7 gauge group, then you have a case where the Chern-Simons number is integral and integral plus a half. And so in that case, you can always find a minimizer connecting them. But in these cases, in the case where you have these, in the G2 and SO7 case, this component is actually a point. And so in that case, you can show you have exponential decay at this end. So life is better when you have, I didn't write that down as a proposition because I think everybody can prove it in a graduate student class. But if these, in the cases where these components, the space of flat connections are a single point, then you can always prove exponential decay at that end for the instanton. Is that what you were asking?
Sort of.
Sort of. All right, then that's sort of your answer. Okay. All right, so let's see. So let me say a little bit about my statement that somehow quadratic decay is critical here. For analysts, this will probably be clear, but as a mixed audience, I think it's worth explaining why I say there's so many proofs for the coordinate decay and why the 1 over r squared decay is harder. I guess first let me say a little bit about what the basic strategy of proof is. So the basic strategy has 2 ingredients. So first, we need some weighted integral estimate for the curvature. Something say that some curvature times some weight function is less than or equal to some constant, so A is some weight function. And here, such integral estimates are going to come from Bachner formulas, so use and Hardy-Sobolev type inequalities. And once you have a weighted integral estimate, then you need so once you have that, then you use Moser iteration, both global and local, to prove local decay. So let me just give you a sample of sort of what you might have in the Taub-Net case. So example for Taub-Net, if you know that R to the A FA is in L2, so if you can prove that level of decay, then Moser iteration will tell you then R to the A plus 3 halves FA L2, excuse me, that's not, well, that would be a false statement. This guy, let's make it a constant times R to the minus A minus 3 halves. All right, so that tells us that we'd really like to prove some integral estimate where A is equal to 1/2. Now, that clearly is impossible though. So this is sort of an optimal statement, but then we have, let's just note, if A equals 1/2, then the statement is that we need, if this is decaying quadratically, then this is R to the 1/2 FA should be like 1 over R to the 3 halves, which if we square it, well, we have 1 over R cubed, R squared dr needs to be integrable, and it's not. So it's not an L1 loop. So even here, this isn't the place I was going to focus on, the criticality of 2, but even here, we have borderline behavior even just for applying standard Moser iteration techniques. And so what we actually have to do is once we get our integral estimates, we get an integral estimate for every A less than 1/2, and then do some non-uniform estimates as we go to infinity. And I don't want to say how that goes on at the blackboard. All right. So let's see. Maybe since I'm low on time, I won't write it down. I'll make a statement that you can always prove with this sort of nice geometry that the curvature is decaying at some rate as you go to infinity. This, sometimes when I have physicists in the audience, I have to point out to them when they say that all these things are obvious, that in the quantum mechanical reductions of Yang-Mills theory, you have ground states which along certain troughs can actually grow polynomially. So it is possible, even with these finite energy conditions and satisfying nice equations, to have some unpleasant behavior. So just mention that in passing. Okay. Right. So now let me say a little bit more about the criticality of dimension or quadratic decay. So when I was doing the crude estimates, linear estimates, I was really solving a standard ODE, or that's one way to do it. So when we were looking at our linear intuition, we were looking at the equation 0 is equal to, minus d squared dr squared plus minus n minus 1 over r ddr plus whatever we get from the radial, the spherical harmonics, so lambda over r squared. And I guess I could put a function in here. So we know this will be some, we get solutions that satisfy a power law. And of course, here we get that P must then be n minus 2 over 2, plus or minus the square root of what? Lambda plus n minus 2 over 2 squared. So back to freshman ODE. And now the observation is the power law depends delicately on lambda. So if you change lambda, it changes your rate of decay. But we've got our Bachner formula, which we had written earlier. That was in the form. So we had 0 was equal to nabla star nabla of FA plus, I'll just write it as F commutator F plus some RF term, so I'll just be sloppy here now. And
It's on your right-hand side.
beg pardon?
On the right-hand side of the board.
Oh, sure enough, it's already there. Okay, so I haven't, I didn't erase it, that was really planned. So I have the Bachner equation here, the Bachner formula, and I'm trying to prove that this is behaving like 1 over r squared. And so this, if you thought of this as my lambda, then I'm trying to show it's 1 over r squared, but I don't know 17 over r squared or whatever. I don't know how big that is. And so this is a 1 over r squared term, and so it's like our lambda here theoretically. And so a priori, a 1 over r squared term can completely change the rate of decay, but I'm trying to get the decay rate of f, and I have a term there which is exactly critical for the decay rate. That's why if you're trying to prove something like 1 over r to the 4th, these guys in our case are worse like 1 over r cubed, and it's easy to check that's not going to change decay rate. And so the 1 over r squared terms are exactly critical and can be obnoxious. And I'm running out of time for saying how we address that. Let me, I guess I can quickly say how one gets around that, but then I won't have time to address the R cross T3 case, which is in some ways cuter. And I think anybody wants to hear about that later. So in the R cross T3, so what we'd like to do is essentially reduce this to the linear case where we have strong information. And so we just want to do a little Lie theory and say that we have, we can think of, this takes values in add E, and we said that add E has a natural splitting now. We have the holonomy of our circle bundle splits add E as follows. We can say add E is equal to the centralizer plus a perp, which for some reason I called B. I guess P would be better for perp. So this is the centralizer of the holonomy. And then we can decompose F as Fz plus Fb. And then in integrated forms, the Bachner formula, when it's integrated, gives us something like this. We have nabla F norm squared plus, we'll have an F commutator with an F, inner product with an F, and let me suppress indices, plus lower order here. And when we do this splitting, we know that since the Z terms, the centralizer terms mutually commute, you have to have at least two B terms here for this to be non-zero. So let me not worry about constants and put a B here and B here. There's some constant here when I do it that way. Probably 3. And one can use the holonomy condition to show that asymptotically nabla Fb squared is greater than or equal to alpha squared Fb squared. Let me at least put in some cutoff function. So let me just say near infinity. Let me localize that in some way that I won't do with 0 minutes remaining. And so what ends up happening is then the terms where you have B's, you can essentially absorb those with an effective potential coming from the connection terms, and the terms where you're dominated by Z's, those just become linear again, and you can use essentially linear analysis, which is really a lie because you have some difficulties with the Moser iteration, but essentially it should work, right? And it does. So you carry it through, and so it's one can break it up. And I've run out of time, so I won't tell you now. You can ask me afterwards about the R cross T for anybody's issue. Okay, thank you.
Are there any questions? Actually, I have one. So do the FB and the FZ decay differently, or do they?
So yes, from this, and somehow FB should be a slave to the FZ. It's decay. If there weren't some interaction terms, this would tell you it decays exponentially, but there are always some interaction terms, so it should be decay like 1 power faster.
One more cubed.
What about the non-generic case?
So I didn't write down for today what the numbers are for the non-generic case. I've got it in my notes somewhere. But again, there's a version of the non-generic case if you assume that the associated moduli space is finite dimensional. So the formal moduli space. Remember my condition on the R cross T3?
No, for this one.
Yes, but I'm saying in this case also there's such a theorem. There's a slightly worse decay rate, which I don't remember off the top of my head. I didn't prepare that for this talk, but there's a slightly worse decay rate that you can prove if you assume the formal moduli space is finite dimensional. And as I said, I haven't finished convincing myself that that seemingly obvious statement is also obvious and correct.
So where do you need to use this condition that the formal dimension is?
Well, that's a good question. I'm glad you asked. I grew up doing a lot of linear analysis and a lot of index theory, and this is a case where I use some technology, some ideas from index theory to bring some new ways of getting estimates in the Yang-Mills. And so the notion was I'll write it this way. So I won't be able to give the details of the board, but we know that when the curvature is self-dual or anti-self-dual, then we know that on certain spinors or on certain forms with given chirality, you know the curvature term will vanish. And so you can think of it this way: there's an operator D, so there exists a D, well, let's just say d plus d star. So d plus d star squared, acting essentially on, say, self-dual forms. Looks like now the star now plus just the curvature terms. No, just the remaining curvature terms. And here you have to be careful because if you have to actually do the d plus d star, not dd star plus d star d, because otherwise you won't see some extra curvature cancellations that come in. But so this looks like nabla star nabla plus curvature, and so you can get estimates on this side. Or maybe, if you want to make it more believable, you can maybe put an R factor in. And get estimates for this operator.
Because you don't have any F.
Because you don't have any F. And then you can say, well, it's an index series you know well, Anna. You can transform the spectrum for LL star, the spectrum for L star L. And so you can use that to you can bump that up to get some nonlinear estimates and actually get estimates from this operator and move them to estimates on the other side. And so that allows you to bypass some of the problems, seemingly all the problems with the curvature. However, you remember when you're doing that index computation that because indices aren't zero, you can compare all the non-zero spectrum. And so it suffices for getting these estimates to have to get these estimates, it suffices to just control the essential spectrum for Hardy type inequalities. And so it's not essential that you have no kernel, but you certainly need to have finite dimensional kernel, plus this guy clearly has a mass gap, or a spectral gap. And so you can use that, as I said, to transfer estimates to get the integral estimates from one side to the other. In answer to your question from earlier, you can play this with different powers of R and find an optimal one that gives you the best possible number, and that was just how the 4/3 and 3/2 came up. It was just sort of the best possible number that I could get under various assumptions.
Okay, anything else?
I mean, you've talked about instantons on very special, very non-generic background four manifolds, which is like multi-tab nut. To what extent are these problems integrable and you get insight
Well,
from
first,
exact solutions or somehow
Well,
some
first-
machinery of
First, let me say that for Taub nut and ALF type spaces, I don't need any hyperkähler stuff to do this. So I need the geometries. What I really need is close to a circle bundle over R3 for what happened here. So nothing of the special geometry was used in constructing this. Special geometry is used heavily in, I didn't get to applications in the moduli spaces, so that someone else will take that burden for us. So we didn't get to the application part of the talk. But for studying the moduli spaces, that's very important. But for getting the decay, it's not important. And so it's certainly conceivable that you could use more of that structure to get the decay, but that wouldn't be I prefer something more robust.
So for early case, Kronheimer and Nakajima have a complete description of the moduli space of anti-circular connections, gravitational distance.
So as I said, in ALE it's all well.
Yeah, but for Tauna, do you have like sort of there's a box?
That's Sergei's talk.
Oh.
And that was my motivation for looking at this, was to understand that moduli.
For the A type.
For any type.
Any type. Exceptional group on D type AV.
Kronheimer and Nakajima, or
Yeah,
I thought it was.
it's A on A.
Yeah, it's, so you are talking about
not generically, A on A. No, Sergey claims more.
Claim in A left. We understand how the spaces. You type A and left spaces.
Okay,